Okay, so today we'll be talking about full automation. And this lecture in particular will be talking about, um, we'll be spending some time talking about how, what we can learn from the distant past in which arguably, we were kind of turning output into more people, roughly analogously to how we could turn output into more robots in a world of full automation. So, the distant past might tell us something about the distant future. Okay, so yeah, to start with, instead of jumping all the way to growth substitution in both sectors, the production and R&D sectors, we can ask, what's the threshold case? Um, where's the line precisely past which you start seeing explosive growth? And it turns out you don't actually even need to get all the way to growth substitution in both sectors. You can just have Cobb-Douglas production in both sectors, and the exponent on capital just needs to be high enough. So how high? Well, as a kind of intuition, as sort of sketch of a proof of the result, suppose capital is proportional to output for roughly um, the usual reason that capital comes from saving some fraction of past output. So capital is going to be proportional to AK to the alpha here. Oh, we're just kind of assuming that labor is constant and equal to 1. I should have flagged that. Which is fine because, like, in an explosive growth scenario, we're talking about mechanics that could unfold before the populations had time to change much anyway. So capital is proportional to AK to the alpha. Rearranging, you get an expression for capital as a function of A, of technology. Then substituting this into our R&D function, sort of 1B up here, you get GA proportional to A to the psi over 1 minus alpha, that's coming from the K term, minus beta, that's coming from the A to the minus beta term. And this makes it clear that technology is going to grow hyperbolically precisely if that exponent is positive, right? And with technology growing hyperbolically, well, output will also grow hyperbolically because even if capital were fixed, that would drive hyperbolic output growth, and then capital will tag along for the ride as it comes out of output. So that's the threshold, and we're going to get exponential growth in all the terms only if the two sides of this inequality are actually equal, only in that sort of knife edge case. If the inequality is reversed, we're on the non-explosive side of the line. The feedback loop here with more capital, meaning more technology, meaning more output, meaning more capital, that feedback loop on its own will only deliver power functional growth. So we're still in the familiar world in which exponential growth would require population growth. Now, unfortunately, I mentioned this was just kind of a sketch and not a proof. And the reason is that capital isn't generally proportional to output here, even under the old assumptions of a constant savings rate, constant depreciation rate. Capital grows like past output. And to kind of sharpen up what I'm getting at here, let's say it just grows like last period's output. Okay, so let's say you've got like discrete time and there's 100% depreciation rate. So it just lasts for one period. That's going to be proportional to y if y is growing exponentially, right? Like, if y is doubling every period and, capital today is half of output yesterday, then capital today will always be a quarter of output today. And if y is growing slower than exponentially, it turns out that you're still going to get this kind of in the limit. Capital is going to be proportional to last period's output. I'm sorry, proportional to today's output. But it'll be, I mean, the asymptotic proportion might be, well, anyway, we don't need to get into the slower case. The interesting thing here is that capital today will be an ever smaller proportion of output today if output's growing super exponentially, because then output yesterday is falling to zero as a proportion of output today. So despite that, the result on the last slide is right. And I think roughly the intuition driving it is still right, but you can work through the proof and see what I'm getting at if you're interested. All right. So we've been thinking separately about production and R&D and thinking about the move from gross complementarity to gross substitution. And here we're kind of finding the threshold case where if you, the line you can draw in the two sectors such that if you're kind of on the other side of the line, you're in the super exponential regime. To tie these things together, what happens if we get gross substitution in research, but we're still Cobb-Douglas in production? That's like sending psi up to lambda, right? You won't necessarily get hyperbolic growth here, but the threshold will be that lambda over 1 minus alpha has to be greater than beta. That could go either way, but it's going to be a weaker condition than yesterday's condition, where if you still have gross complementarity in production, lambda's got to be greater than beta on its own. That was a really strong condition, right? I was saying that doesn't seem like it's held historically, unless maybe you look at like Moore's law in isolation and assume no spillovers and stuff like that. So yeah, you can make that case, but it's at least far from obvious that that this would suffice. But in combination with a bit of automation in production, such that we get up to just on the edge of gross substitution, we're in the Cobb-Douglas case, and in particular, we're on a relatively high alpha side of the Cobb-Douglas case. You know, the thing on the left there, that's not going to be lambda, it's lambda divided by something less than 1. It's going to be bigger. So it's going to be easier to fulfill the condition. Right, because before gross complementarity in production, that's kind of like assuming alpha equals 0, right? Output just grows with labor involvement, if that's a scarce factor, because you've got sufficient safety. If you just have gross complementarity, gross substitution in production, and there's no resource constraint, that's like sending alpha to 1. And as we saw, if you have like an exogenous exponential rate of tech growth, you get double exponential growth because you got AK, robots building robots, and then how many robots a robot can build in a year is itself growing exponentially. But here it's actually even faster than that because how many robots a robot can build in a year isn't just growing exponentially, it's growing at a rate that itself is growing as the capital inputs to R&D are growing, and that feeds on itself, and you get hyperbolic growth as long as that exponent on capital in R&D is positive at all. I say beta greater than 0, but obviously if beta is equal or less than 0, that only makes the growth faster, right? Beta equals 0 is the Romer case. And then, of course, if you've got gross substitution in both, then the inequality really has to hold, right? Yeah. I mean, it's just a generalization at this point. Alpha equaling 1, left-hand side goes to infinity. So whether you've got a psi or a lambda on top, it's going to be bigger than any beta. Does that make sense? And it's just like structurally, the setup of this problem is there's only 3 outcomes, right? Once you flattened it down to a single differential equation where you've got like y dot equals y to a power, or k dot equals k to a power, or a dot equals a to a power, the power can be greater than, less than, or equal to 1. So, you know, if it's faster than exponential, which is what it is with no tech growth, but full automation. If it's faster than exponential here, you know what it's going to be. It's going to be hyperbolic. I don't think this is like a deep fact about the world. I think this is kind of an artifact of the functional forms that we're using. The super exponentiality is a more fundamental point, though, right? Like robots building robots is an exponential process, and then something on top of that will be super exponential. But in models of this form, it'll be hyperbolic. Obviously, given the Romer case, you also are guaranteed a hyperbolic growth. But here it's kind of because the thing that's exponential without any help is R&D. And then you add on top of that the fact that you've got an ever-growing number of virtual researchers or robot researchers. And so it's got to be super exponential, right? Fixed number of people, exponential R&D. So, if it's super exponential, it's going to be hyperbolic. Yeah.
Or do we get daily exponential growth? So steady level?
Yeah, that's a good question. So there it depends how fast how fast A is growing. It definitely won't be, unless we just totally halt research, it'll be super exponential, right? But it'll be yeah, but there how super exponential it is will just depend on like how fast the population is exogenously growing or the population of researchers is growing. If you have say a constant population and you've got gross complementarity in research, that's going to be power functional growth in A, right? Now the growth rate at any given time is basically going to be A. It's like how many robots or like SA, savings rate times A minus depreciation. And so for any finite growth rate, if A is growing without bound, the growth rate will exceed it. But the growth rate could be growing like linearly or whatever. But here we're not assuming population growth. Here we're assuming population stagnant. That's what's making it just an invisible constant. And in that case, yeah, constant population means power functional tech growth, which means, yeah, okay. So I guess that's not going to fall into one of these three cases. It's going to be super exponential, but the growth rate grows power function. Okay, with that in mind, I want to talk about an argument that this is basically the world we were in the distant past, but where it was humans rather than capital that were accumulating with past output. And, so the human population was growing super exponentially. And what we might be able to learn from that when we're kind of putting our robots to work in a Malthusian-ish way. But before I do that, something I forgot to do, I don't know how to get out of this, is go over that bit of yesterday's second lecture we were talking about bottlenecks to research, right? We went through a few, but we didn't go through the last one on creative destruction. I think it really does deserve a mention. So sorry for flipping back and forth here. Okay, first, just for some context, because I think I might not have set it up very well, taking even a further step back, some context on Parker's research, Parker and Charles' research on whether cognition and compute are gross complements in AI R&D. This is, in a way, structurally similar to the parallelizability point, but it's putting the bottleneck into the R rather than into between A and R. You see that? So they're just separate. You could put it in either place or both. And I guess the other thing I wanted to say on this was that just because it's so different from what we've been seeing elsewhere. Um, it's worth kind of highlighting how odd it is, maybe. The thing that's potentially bottlenecking a growth explosion or an intelligence explosion in this model is a lack of compute rather than a lack of effective people. So it's really flipping the whole kind of bottleneck story on its head. We're saying we'll be bottlenecked by a lack of capital. Typically, we're bottlenecked by a lack of labor. But what happens if we can scale up the amount of effective labor by loads because we can simulate researchers and we can simulate ever more researchers per unit of compute. So now like that bottleneck's been relieved. And it's just like yet another case of thinking, we've relieved this bottleneck and then potentially hitting another bottleneck that we haven't needed to account for this whole time, the lack of lab equipment, in this case, experimental compute, um, which has been growing in tandem alongside what we had been thinking of as the scarce factor. Um, that makes sense? I don't know. Maybe you all got that, but I thought that context might be clarifying for some people. Okay. Yeah, a final potential bottleneck to the speed of R&D, even if we fully automate it, is like this whole field of growth theory, this whole class of models called Schumpeterian models, in which really take seriously the point that research will only happen if someone kind of can make a profit by doing it, which we've totally been glossing over, right? Like we haven't think about that at all. We just say like a dot's a function of inputs, and okay, but like why? Who's doing the input? Um, and yeah, it's a shame. I spent all this time on this parallelizability thing. That's just something I thought of a month ago, and then this is like this whole giant field of growth theory that I left to the end. But to get the intuition, let's say you can think about it for a particular good or for like all of output. So either way, let's say you've got a good that's got unit elasticity of demand. Every time its price halves, it's or every time like our productivity at making it doubles, it's the quantity demanded doubles. You see why this has to hold for output as a whole, right? Um, fixing budgets, if the price of output halves, then quantity demanded will double for supply to equal demand. Or for budgets to be exhausted. Okay, now let's say you've got an entrepreneur that spends, some innovator that spends RI units of resources per unit time on R&D. Let's say in that case, his probability per unit time of discovering a more efficient method of production for this good is RI. So there's no diminishing returns here. You could introduce them. This is just the simplest possible model. So double your spending rate, double the probability per unit time you find a more efficient method of production. What that means is that the innovations you discover are coming as like a Poisson process, and the expected length of time to your next discovery is going to be 1 over Ri. Is that kind of intuitive? Like, if the probability per unit time is like, once per year on average, then like your expected length of, or is twice per year on average, and the expected length of time for discovery is like 6 months. At least sort of roughly that should make sense. And so what that means is that the expected expenditure until a discovery is 1, independent of the spending rate. If you double your spending rate, your money's going out twice as fast, but you hit a discovery in half the time. And the discovery will increase productivity and thus sales by 1 unit from whatever the baseline is. Okay, so this is unrealistic, but the idea is like whenever the discovery shows up, at time t, at some time t prime, the productivity level jumps up by 1 unit from whatever it was at the time. One reason that's unrealistic is like, let's say you start out working on some more efficient method of production while the current state of the art is A0. You're just trying to beat that current state of the art. And let's say you finish your research effort randomly after like 1.7 years. But in the meantime, someone else finished a research effort after 1.6 years. Then the state of the art as of t equals 1.7 is A0 plus 1. And when you become the leader, you push up productivity by another unit again to A0 plus 2. See that? So basically, you stand on the shoulders of the A0 plus 1, even though that discovery didn't exist for most of the time you were working on yours. But anyway, just flagging that this is a simplifying assumption, even though it's not, it's not really so sensible. So starting from that t equals 1.7 or whatever, your discovery gives you a monopoly until someone else discovers a more efficient method. Why? Well, it would be inefficient for the people with the less efficient method of production to be doing any of the producing, right? Like you'll be able to outbid them or, in equilibrium, precisely bid match them on any sales they might want to make. And the profit you'll be able to make per unit time is exactly that gap between how much output the nearest competitor would have been able to offer a prospective buyer and how much you can now produce, right? You just get to keep that difference. And we're saying that gap is 1. And again, just to make this as simple as possible, let's say that everyone is risk neutral in resources and doesn't discount the future. The first thing to realize is that given that someone does R&D at all in this model, they're indifferent about how fast to be spending. Because the expected length of the monopoly that they hold, assuming that once you've got the monopoly, you spend nothing. So if you're going to be displaced, you're not going to be cannibalizing your own market by like spending R&D and then spending money on R&D and then replacing yourself and then getting 2 units of profit instead of 1. You'll be indifferent to that. So it's without loss of generality, but it makes things simpler. So let's say I spend nothing. So the duration of your monopoly is governed by how fast everyone else is spending. You see that? If there's no one else doing any R&D, your monopoly will last forever. But if people are doing R&D really fast, well, if the total that they're spending on R&D is R minus I, say, for everyone else, then the expected length of your patent being at the cutting edge is going to be 1 over R minus I. So that's the benefit of doing R&D. And the cost, it doesn't matter because if you spend twice as fast, you get the monopoly kind of sooner. But you're spending, like let's say you spend twice as fast. Less. The amount that you spend to get that patent is going to be the same because you've got to be spending twice as fast, but you're spending over a length of time that's half as long. Does that make sense? Okay. So given that someone does R&D, they're indifferent about how much they spend. But to be indifferent between entering and exiting, right? So that you don't have like everyone wanting to be an entrepreneur or no one wanting to be an entrepreneur. The expected duration of monopoly has to be 1 because the cost of getting a patent is 1, no matter how fast you're spending. You spend RI per unit time, and then you're spending it for 1 over RI units of time in expectation, but you're risk neutral in resource. Okay. So in equilibrium, the duration of monopoly has to be 1. which means the total spending has to be 1 all the time. So let's say there's 2 people, and you spend at 1 unit per unit time, and then you get the monopoly and you stop, and the other guy spends at 1 unit per unit time, and then he gets the monopoly. So in equilibrium, A is going to grow linearly at 1 unit per unit time on average. Do you see that? Because the staircase is rising. Every step is 1 unit high, and the widths of the steps are an average of 1 unit wide. So like the slope is 1 when you zoom out. The key point about this model is that innovations have to arrive slowly enough to incentivize developing them. It's sort of a paradoxical sentence, but internalize it. And how big an issue this is will vary by industry, but you might think it's an especially big issue for tech with low switching costs, so that once you get your monopoly, there's not like a lag between when someone introduces a better version and when it's adopted, because everyone's got to switch over. Maybe they're not even going to bother switching over if they think you'll come up with a better version soon anyway. If people instantaneously switch, the expected duration of monopoly might be low, and the profit maximizing rate of investment might be low. I mean, we haven't really gotten into that because the model's so simple, but hopefully the intuition is clear. Okay. Let's say we retain the assumption. Any questions on that? Okay. The Schumpeterian growth theory. And again, it's like a giant literature and there's books and books, but the seminal paper, the seminal discussion is by Schumpeter, but the seminal like mathematical treatment is by Aghion and Howitt, 1992. What made Aghion famous. Yeah.
I suppose like element that is like mostly focused on like inference rather than efficiency. If I suddenly
Rather than what? Efficiency. Yeah, yeah. I'm not sure I follow. To clarify, what I mean is, let's say you've got a bunch of users paying you your 20 a month for GPT plus. Yeah, yeah. Then the users will switch over. What if we retain the assumption that everyone's elasticity of demand for this good is 1, but now there's not like a total total budget of 1, but it's like 1 per person, but the population is growing at some rate GL. So roughly the implication is going to be that the monopolist now earns a profit of L per unit time, because they get to like, they're selling to everyone and they're selling 1 unit per person, and they're making this much per person. And so to be indifferent between exit and entry, the expected duration of monopoly has to be shorter, right? Because they're still spending 1 unit, one like $1 for a new patent, an expectation. It's 1 over R times R per unit time, 1 over R units of time before you get the patent. Or the trade secret or whatever. But to pay that back, you just need to have the monopoly for 1 over L units of time, because you're making L dollars per unit time. And so 1 over L, that's shrinking exponentially, right? And so the innovations are going to have to come faster and faster. And R&D expenditures likewise will be growing at rate GL. So larger populations here can drive faster growth, but this will be driven by the market size effect. It'll kind of all be on the demand side rather than the supply side. It's not that larger populations are necessary for R&D, and we're already sort of maxing out at the feasible rate of R&D. We could have had faster growth all along, but it just wouldn't have been profitable. And then it becomes profitable because of the larger population. It's a totally different mechanism from population growth to faster progress. And in fact, not only was faster growth feasible all along, it was socially very desirable all along. In this example, in some sense, it was infinitely desirable all along because I stipulated that people don't discount the future. So any finite cost now, getting you, getting you more output, being the time forever, you're sort of willing to spend, an infinite amount. I mean, it won't really be defined because you have infinite utils even at the baseline. So the simplification starts to break down a bit, but the point is the limiting factor is this like equilibrium thing where innovations have to arrive slowly enough to incentivize developing them. The limiting thing is not a lack of potential research inputs. Now, as I was saying, even though intuitively it sure seems to me like LLMs have those low switching costs, and so this would be a really big issue in that industry, and there's a lot of commentary to that effect. A working paper just posted recently by Andre Fradkin argues that actually maybe that's not exactly right. When you look at the introduction of a new model, it very quickly cannibalizes the existing company's old model, which makes sense. It's like kind of maybe sort of the same thing but better. But when a whole new model gets introduced, like DeepSeek or Gemini, total usage just rises without actually cutting into the usage of existing models much at all. So this is a more favorable story. And this is a story in which you have kind of, expanding varieties or something. And you don't have the tech all basically being the same and it just being a race where they're stacking up on top of each other, like in the pure creative destruction model. Again, you can find commentary of people saying, maybe even if this is right now, it probably won't stay that way in the future. But yeah, interesting analysis from the opposite perspective. Okay, so let's say that's how the world works when we automate R&D. What changes? We're not automating production, right? We're still in yesterday's world where we automate R&D but not production. What changes? Anyone know? What do you think? What do you say? Nothing, because this is already a lab equipment model, right? The input to R&D was just an expenditure. You could think of that as, giving up some output or some capital. Yeah. What would change the growth rate is if R&D gets cheaper relative to production, right? So if now the capital, say, that you're using to come up with these new patents is like you need half as much of it, and you could be using it in production instead. And so, or like the output you're diverting to come up with a better model, we need less and less output given up. This would be a case, maybe you need, a fixed amount of compute to come up with the next model, and the price ratio between computations and other things is falling because of Moore's law or whatever. So in that case, every time, like I say, R&D, the price of R&D falls by half relative to production. Now, the equilibrium condition is that the expected length between discoveries is 1/2R. Sorry, no. Now it'll just be the case that the expected length between discoveries is 1/2R, because each unit of R spent is producing discoveries at double the rate. And so the equilibrium monopoly duration is going to be a half, and so growth will be twice as fast. Yeah. But the reverse can also totally happen. Like it can be that we come up with ways to use capital to make final goods more efficiently, but we don't come up with ways to use capital to do R&D more efficiently, right? In which case, it just goes the other way. Yeah.
We have some background of public investment
It can work that way. I think the way people more often think of it is that you have public investment in like basic research, and then when it comes to actually developing final goods, those are governed by dynamics more on the Schumpeterian side. I'm sure you could write a model. Maybe someone has written a model where they're additive. Uh, yeah, it'd be interesting. I'm not familiar with one though.
You didn't put any questions, but Maxime put in content, which seems maybe relevant. The Schumpeterian perspective seems to hinge on the assumption that the primary motive behind the innovation in AI is short-term profit and not some long-term dominance in the sector. Are the companies even profitable as of now?
Yeah. Right. Well, no, exactly. The companies I think are still not profitable. And that's exactly right. They're hoping to get that moat or whatever, or get that big leap of a staircase that lasts for a long time. That means that they can that they can earn profits for a while. They can charge a lot for their model because the next best model is a lot worse, and you can see concretely how that might happen in AI in particular, because if we're using AIs to like help write the code and do the experiments and make better AI, then a company that starts out with a little lead, it can quickly turn into a big lead. And so like their innovations might be coming faster, and it might be a while when they get a lot of profits. Yeah. And funnily enough, I had figured, well, why would a company just use its own model? Like it can just use anyone else's model. But no, they only use their own models because they don't want to reveal secrets, right? So this is very, in any other industry, you just use the best model. But in AI, if you don't want to leak your secrets to the competitor, you've got to use your own model. And so you have this like firm by firm feedback loop, which so far has been, it's kept the models sort of growing, their quality growing roughly in tandem, but that's not a law of nature. I don't think it could get out. One could spiral way ahead of the other. Yeah. Even worse, if AI speeds up precisely that kind of research that most slows down everyone else's incentive to innovate, then the equilibrium growth rate can slow. This is pointed out in the appendix of that Aghion et al. 2019 paper, which is a great paper. It does many things at once that aren't really related to each other, but they're all great. And this is the same paper that like introduced that simple task-based model that we went through on Monday morning. In the appendix, they point out that something like this might happen. So this is my simplification of it. But let's say for any given production technology, some individual is randomly the lowest cost producer by a tiny bit. Okay, so for everyone else, A is how productive they are at making the final good. But for some person, for whatever reason, their cost is 1 over A minus 0.1. And let's say someone can spend on a certain kind of research, which is business feeling research. So it's learning to like copy what someone else has done. Maybe in the LLM case, this would be like distillation or something. Once a model's already out there, you can put a bunch of, you can spend a lot into copying the model by just training your model on the outputs of the other model or something. But it's could be just like reverse engineering in general or whatever. Let's say AI facilitates reverse engineering more than it facilitates normal engineering. All right, so let's say before AI, we're not that productive at doing this kind of copying tech. So this person with the mild advantage, once they steal the tech, I say steal, obviously it could be perfectly legal, but once they steal the tech, they're going to be able to undercut the people who developed it only by like 0.1 units per unit time. And if they'd have to be spending a lot to do that distillation or whatever, that might not be worth it. So they might as well just spend their R&D budget on like a real discovery that gets them the whole one, the whole step of something kind of genuinely novel. But then after AI, let's say we get 20 times more efficient. So now they have to be spending, like if they're spending R hat at rate R hat, they're going to have to be spending for 1/20th the time. And then that makes it worth it. Okay. But everyone realizes that if they innovate, their innovation is going to last for a really short length of time, unless, once in a blue moon, they happen to be the lowest cost producer, right? Then no one's going to be out there that tries to steal from them. And, anticipating this, the equilibrium rate of innovation will be really low. Maybe a closely analogous dynamic is this point some people have pointed out that what with LLMs, there's less of an incentive to generate new tokens. There's this graph I maybe should have included on Stack Overflow usage over time that once, as we introduce better models, people pose fewer questions on Stack Overflow, but that means less new data for the models to train on in the future. And so maybe we need to incentivize people to create new tokens of a certain kind. I guess Eric was kind of talking about this before in the call center context, where you want to now you have to go out of your way to actually invest in your senior customer service representatives or whatever. Once again, we identify a bottleneck we might not have thought about before. One lesson is that growth might not grow so much in the event of automated research, but the other side of the coin will be maybe this is a new channel through which growth could be sped up, right? So in a way, this is a coordination failure, right? If we're growing way slower than we could and than we want to, because we can't all coordinate to pay off our potential innovators enough to do more research than would be possible given the speed of innovation that would induce. That's a coordination failure, and maybe AI could help us overcome it. So in the kind of extreme case, maybe you've just got robot entrepreneurs that can do research on their own. They don't need a monopoly incentive. And they're all kind of publicly owned, and we just tell them to go off and innovate away. Yeah.
Just as a comment on the Maxim's point, the long-term profits, or also in general, I think Schumpeterian models are very large class of models, just like we've been discussing the CS production function, and we considered every case where the increasing resource scale, you have also incumbent innovations, you have incumbent and the engine competing, incumbent, increasing the gap, and basically you can get all sorts of conclusions in terms of,
Absolutely, yeah.
whether you're in for the long-term profit. So again, it's a very highlighted model.
Yep. Thank you very much for emphasizing that. Yeah, this is why I really wanted to cover even the 4 slides I had on this, because if anything, it could have gotten a whole presentation. But there are a lot of assumptions baked into this model, just kind of either for simplicity or just because there's a choice point, you need to pick one. One of them here was that you have no advantage to improving on your own product. There's no incumbent advantage. And I was saying before, with using an AI model to help build a better AI model, dynamics like that, for instance, can kind of give the incumbent an advantage and will mean that they don't just want to rest on. It's not most possible for them to rest on their laurels. So, yeah.
And even the last sort of extreme case, don't we just see it with companies when they achieve sort of consumer scale, and they sort of have learning by doing improvements? And I feel
Yeah. I mean, as came up before, it's always hard to distinguish pure learning by doing from just the observed correlation that when you are growing, you can afford more R&D, and when you anticipate to grow more, then each unit of R&D will be saving you more money because you'll be selling more units. But yeah, I mean, we certainly observe that, even when they have a lot of market power, incumbents do innovate. And part of that might just be mechanical, they do pure learning by doing. Yeah, I think it's sort of the embarrassment of riches. There's too many theories that can explain it. Yeah. And yeah, I'm sure there are people who have put their growth theory hats on and really dug into the LLM market and have a better model of it than I do. Yeah, but I'm just so maybe we're especially interested in the AI case, and but this is all I have to say about it. Y'all should look into it. Yeah, thanks. Oh, it seems like we do have something in the chat. I'll take a look, but just a reminder. Oh, this is the same comment. I see. All right, so back to. I've already taken all the time, so let's take a break now till 12:10. Let's take the full 15 to 12:10, and then get back to Malthusian past. Okay, so we were thinking about that Cobb-Douglas threshold that we need to cross to go from a world of sub-exponential growth, fixing the population, exponential growth sustained only by population growth, to one where capital drives super exponential growth. Now, I was saying there's this argument that you can learn about that world by looking at the past. So before the Industrial Revolution, it seems that populations grew super exponentially. Okay, they were growing really slowly. The exponential growth rate of the world population was low, but it was rising over time. And consumption per person was basically constant at the level needed to keep people alive. Michael Kramer has his 1993 paper offering a Malthusian model to match these facts. And yeah, hopefully it's intuitive how it can shed light on growth under full automation with capital replacing labor. Labor was basically doing, according to this story, labor in the past was evolving the way that we might expect capital to evolve after full automation. We create more output. Output, it tastes like calories, and then we just turn some fraction of those calories into new people. It's like building more capital, and that allows for more innovation and more production in the next period and so on. Yeah.
So these models, we concluded whether the growth is exponential, super exponential. Was it a balanced growth path? And
what do you mean? What do you mean by these models? When we were talking about after the Industrial Revolution, we said, let's say population grows exponentially, and you get this balanced growth path where output is also growing exponentially, but at a faster rate. So output per person is growing over time. That's all post-Industrial Revolution. We're talking about before. Yeah.
I guess we can observe. So, okay, my question is just, do we say, population is growing super exponentially due to some, whatever factor, or is it that there were some constraints that were such as famine, etc., that are now relaxed? I guess.
So let's say we keep the basics and we say that output is Cobb-Douglas and there's a land constraint. So how much each extra person contributes to the production of calories or whatever falls as the population grows because we're being crowded into ever more land. We've got our old Jones or Romer style tech production function. The beta can be positive or zero. And as we've seen before, instead of having an explicit share of people doing research, the idea is just that every now and then people have new ideas. If you want to have that explicit research share, it's not really going to change anything because, well, we saw this, right? But you have an S here, and that will just be an S to lambda, that'll be a constant, you roll that into the theta. Yeah. Okay. In the Jones model, we were saying that population grows exogenously. But here instead, we'll say there's a subsistence level of output per person, little y bar. And so y over L always equals little y bar. And implicitly, what's going on here is that if output per person if we were off path, so we had not enough calories to sustain the population we had, then there would be a famine, right? L would fall and output per person would rise because now, there's the land's less crowded and the, people can produce more food per person, and the population grows. And obviously, the other way, if we have abundance, then more children survive, people die less often of famine, and the population grows until the equality is met. But for simplicity, we'll say these effects are instantaneous, right? Because we're going to be zooming out and looking at thousands, millions of years of history, and 1 or 2 generations in the transition dynamics will not, they'll be like the blink of an eye. Okay, so that's what's justifying this y over L equaling y bar assumption for a Malthusian world. Yeah, there's no capital here. There's no saving. Output per person is consumption per person. Okay. Just as an aside, subsistence is about survival. Technically, it doesn't really have to be about anything in particular. It doesn't, a world in which we just maintain constant y over L for whatever reason, because it was just enough to survive plus have some amount of luxury or whatever. All the proportions would stay the same. The whole system would evolve in the same way. It's not really about anything in particular, and it's certainly not necessarily about welfare. A world in which everyone's at subsistence is not necessarily a world in which everyone's at sort of zero welfare, like just equivalent to death or something. Now, there is an interesting sort of sketchy argument that suggests that maybe they should be similar. The idea being basically that maybe the creation of pleasure and pain themselves cost some calories. Yeah, and so if you're kind of sort of the most efficient set of pleasures and pains to produce that'll produce the same patterns of behavior in the organism will be ones that are kind of centered around zero, because it's going to be more costly to produce plus 10 when things are good and plus 8 when things are bad than it is to produce plus 1 when things are good and minus 1 when things are bad, because you're not wasting 9 units kind of on average all the time. But anyway, I think that's kind of fun, and you can look into it if you're interested. But we're not going to think about welfare. Okay. So we can write the population as a function of the technology level, right? L of A will be the maximum population sustainable given technology level A. So if output is AL to the alpha, output per person is AL to the alpha minus 1, and then you rearrange and you get that the population you can support with tech level alpha, tech level A, is A over Y bar. You can read it as Y bar over A to the 1 over alpha minus 1. And then you flip them. Right, so this is just our Cobb-Douglas model of full automation, but with K in place of L. Alpha is the exponent on labor now instead of on capital. And you've got the land constraint just as before. You could have a land constraint or some combination of a land constraint and a labor constraint. Yeah.
I guess what I was trying to say, if you're using this model to make any conclusion about the pre-industrial evolution of the world, I feel like we're loading everything related to institutions and feudalism or the tyranny to A.
Maybe I think I would probably want to roll it into A in this case. The institutions that I was sort of not saying I didn't like this before, but at least on some institutions seem pretty clearly analogous to A here, like agriculture or something, survived in the long run because it allowed for more people than a hunter-gatherer lifestyle. And likewise, if you have some contest over time between empires, the ones that can support more people will tend to beat the ones that can't. And there is all this data going back, like the Madison project tries to look at how many calories people were consuming in different parts of the world, and tries to convert the other things they were consuming into sort of calorie equivalents in various ways. Obviously, not all the land was used to make food. Most of it was, but some of it was used to make cotton that was turned into clothes and whatever. So you try to come up with some sort of nuts and bolts consumption equivalents across regions, and they were pretty similar, I think. And oh yeah. So in some sense, this is a fully endogenous model, regardless of what the beta is, because the population is endogenous. Sorry. So we've got L as a function of A, and we've got technology growth as a function of A and L. So we can get technology growth as a function of technology, just sub L in there. And something, sorry, you can do that. I think we'll do that in a moment, but something else you can do is you can get population growth as a function of population. Right. So GL is going to be 1 over 1 minus alpha GA. But GA is a function of A and L. Okay, so now we've got GL as a function of A and L. And because we can get A as a function of L, we can plug that into line 7 and get GL as a function of L. Okay. So this is GL as a function of L. So, we'll get our classic triplet of cases, exponential, hyperbolic, or power functional, depending on these exponents. And it's basically just what we got before, spelling it out a little bit more. GL is going to be proportional to L to a power. Let's call that power phi. This is just the thing that has to be positive. If you remember that thing on the very first slide that was in red, here I'm using a lambda instead of a xi, but it's like, I was saying there's some threshold, right? And if that threshold, if on one side of the threshold, you get hyperbolic growth, right? Here the threshold is phi being positive. Then you get a growth rate that itself rises over time, and it'll be hyperbolic. This is what the shape of the function will be. This is spelled out in an endnote of lecture 6, but at least qualitatively, hopefully this is familiar. And as before, if alpha is 1 or near 1, and or if that rate at which ideas get harder to find is 0, you're guaranteed to have hyperbolic growth. Because like in this case, you get exponential growth even with no tech, right? And so the technological development has to get you into the super exponential region. And in this case, you get exponential growth even with no reproduction. And so the reproduction gets you into the super exponential region. And you can see from this formula what the vertical asymptote will be. We're raising something to a negative power. So, right. So I said there are 3 cases, right? The 3 cases are phi equaling 0, phi being positive, or phi being negative. This is going to be power functional if phi is negative. If phi is positive, you're raising something to a negative power. So there's going to be some t star such that as you approach that time, this difference goes down to 0. And so the difference raised to a negative power is shooting up to infinity. So you just say, at what t is this thing going to equal 0? And that's what it'll be, right? If t equals that, divide by phi m, you get L0 to the negative 5. So the difference is 0. Okay. So historically, what has been the relationship between population sizes and population growth rates? I'm just pulling the equations over to this slide again. The theory predicts that population growth rates will be proportional to population levels raised to a power. And Kramer stitches together a bunch of, very sketchy data, and people have picked it apart a bit since then. And but he finds that before we got to the Industrial Revolution, when the population growth sort of started capping out at 2% a year or something, obviously it's fallen since then. But before that, you had this relationship where larger populations coincided with higher population growth rates. And maybe the power wasn't just positive, which is all you need for the hyperbolic case, more population, faster growth rate. But it was like 1 or even a little greater than 1. See that? Now, as Karan, where is he here? Yeah, as you pointed out 2 years ago, when I kind of presented on this in Oxford in a similar program, this relationship might seem kind of stronger than it is from the fact that, like, the paper is, population growth and technological change 1 million BC to the present. But like all these data points are just right in the run up to the Industrial Revolution, basically, right? Because like the population wasn't anywhere near 1 billion back when we were, hunter-gatherers starting to transition to agriculture or whatever. It's like, yeah, more kind of really making use of that big 1 million-year number. That's all the kind of really, really sketchy data down here, right? So you could also interpret history as basically being like maybe like kind of flat, no growth, and then a little burst leading up to the Industrial Revolution, and then another phase change at the Industrial Revolution where we stopped having ever more children. And but anyway, it's a good point, but this is Kramer's graph. And if phi greater than 1 is yeah, not just hyperbolic, but like really extremely hyperbolic. Even just phi equaling 1 would be the parameter you get in the like full original Romer model with beta equaling 0. So idea is not getting harder to find at all, and there being no parallelizability constraint at all. You see that?
Another comment from Maxime in the chat. Interesting side note. The need for human capital accumulation induced demographic transition. The effects of AI in the labor market and that they increase the need for low human capital jobs might favor more population growth.
That is a good point. Yeah, hadn't thought about that. So he's maybe referring to this Galore and Weil idea that the reason why we stopped turning all of our food into more kids when we started industrializing this is called unified growth theory. It's a view that the reason why we made this shift, or at least a reason, is that when the world started changing really fast, the way to most I might be misrepresenting this slightly, but basically the way to get the most out of your kids wasn't to just have a lot of them, but it was to have a few that were well educated. And so you have to not have as many so you can afford to educate the few that you have. And if that's kind of what's continuing to happen is like education gets more and more in demand because like as the world gets more technologically sophisticated, maybe as the rate at which the world's changing is accelerating, we need ever more education, and to afford that, parents need to have ever fewer kids. That could reverse if like you no longer need skills, right? If in that sort of in that period where we've automated the R&D and we're all wearing the glasses that are telling us what to do, then maybe in some sense the efficient thing will be to just crank out the kids again. I don't think that's the main reason why people are having fewer kids, and I'd be surprised if everyone just switched over to having lots of uneducated kids anytime soon. But yeah, could be. So yeah, so in the past, it looks like growth maybe was like population growth was like super hyperbolic. I don't mean super hyperbolic like super exponential. I just mean extremely hyperbolic. How do we reconcile this with the more recent evidence that by like way less than 1, lambda over beta isn't like infinite, it's like a third? Well, you could think the early data is very mismeasured. You could think that the parameters have been changing over time, like rising beta as we approach some sort of like technological maturity would be this would be really analogous to what Tom Holden and Tom Davidson do in their software intelligence explosion thing, where beta is not a constant, but there's some ceiling, and so ideas don't just get harder to find, but the rate at which they get harder to find itself rises over time as we approach the ceiling. As I'm saying here, if tech has an upper bound, beta can't be constant, or else you can always just we can always keep growing, even if at a slowing rate or whatever. Just going through the parameters, another thing that could in principle cause this change would be if like natural resources are becoming ever more binding of a constraint. But they haven't been, right? The natural resource share is still really low, and if anything, it's lower than it was in like medieval times. I think this is also something that came up. Of course, there's lots of other ways to reconcile these points. Maybe, you know, the Carlson view is right, and the caveman didn't have red tape or something. This isn't really evidence for the view, though, because even though it like confirms a prediction that the Malthusian model would make, it's purely correlation. And it's the same correlation that you would get on any theory that posited that over the distant past, the population growth rate rose. Does that make sense? If population growth is rising over time for whatever reason, later in time, you'll have larger populations and larger population growth rates. So you can correlate them, but it's not telling you why population growth is rising. Something at least a little bit closer to causal evidence is the observation that if you order regions about which we have data by their like initial population size a really long time ago, and you look at how fast their populations grew from then on. Sorry, and these are like disconnected regions. So we're trying to find regions where there were like no technological spillovers, or very, very little technological spillovers between them. The big one started out with larger populations, but their populations subsequently grew faster. And like very concretely, they grew faster because they developed agriculture sooner and they developed cities sooner, so on. This is like a point really elaborated on by guns, germs, and steel. Yeah.
Is that a way to microfound the fact we always have this constant population to ratio where something like, you know,
Wait, population to output ratio in the past?
fast, yeah. So
No, the Glore view is that it starts out Malthusian, but then we shift. Basically, it's not worth even investing that first hour into education when the world's moving really slowly. And then once, but because population is growing and it's growing ever faster over time, and technology is changing ever faster over time because of the Malthusian loop, and the returns to education increase in the rate at which the world is changing, because you can no longer just like pick up rules of thumb from grandma at home, but like you have to actually learn about how the world works in a more formal setting. The returns to education rise. And so we break out of the Malthusian.
we always like double games and opposition routine, and it pays to have that many kids with this spec is changing so slowly.
Yeah. Okay, so that's Kramer's Malthusian model, and so you might take that as some evidence of the limited evidence we can have about what the world would look like with full automation across the board. You can also just do a theory-free projection of like how growth has unfolded in the past and try to project that forward. One early attempt at that is Robin Hansen's 2000 sort of proposal that maybe output has grown over the past as like a sequence of exponentials. So the growth rate has risen exponentially. There was an exponential growth rate for a while, and then you hopped over to a higher exponential growth rate, and so on. And that's happened a few times now already. In fact, with each hop, the growth rate he proposed has gotten multiplied by a factor of 20. So I think this kind of puts the possibility of explosive growth in perspective. Like when you're thinking about whether the growth rate now will rise from 2% to 40%, that would be like one more step of something that seems to have already happened many times already. And yeah, so he ends up getting a kind of overall degree of returns to scale that's like, 1.4 or whatever, which is interestingly kind of similar to it's much lower than the Romer one. But it's kind of similar to what you would get if you thought like you have CRS production and like lambda over beta of like a third or something, right? Because then you'd have GY proportional to Y to the 1/3. Anyway, and then yeah, this totally naive extrapolations like, okay, the next shift will happen like sometime this century, but then the next will happen very soon after that, and then next will happen soon after that. This is basically a hyperbolic process, but just cut into chunks. And it fits the data better than the like hyperbolic pre-industrial revolution exponential after model that I've been working with so far, and much better than trying to like fit all of history to like a simple hyperbola. But of course, it has way more free parameters because like he's separately estimating a growth rate for each chunk. Anyway, David Rudman does a similar sort of curve fitting exercise. He confirms that at least over the distant past, it looks like population and thus output grew hyperbolically. Basically, he just sort of fits the data to a model of the form that we've been looking at, which has to either pop out a best fit that looks like a hyperbola, like an exponential, or like a power function. And given that growth was super exponential at all over most of history, the best fit is going to be hyperbolic, right? But it's not going to pick up like if there was a kink at the Industrial Revolution or whatever. And or if there's like some trend in the variables, because like beta's been rising or something. It's a very complicated paper and it has all sorts of bells and whistles, but actually they're not that relevant, I think. And fundamentally the paper reduces to like deciding whether the past looks more like a hyperbola, an exponential curve, or a power function. And he's like, okay, if you've got to pick, then I guess exponential, then I guess a hyperbolic. And then Tom Davidson has an extension to Rudman's paper, which also does not fix what seems to me like the big limitation, which is that fixed phi on the, once you reduce all the equations to the one line L dot proportional to L to the phi, you're still kind of getting at some fixed phi estimate. And then, the question is whether it's greater than 1 or less than 1. So anyway, if you were going to fix that, you would do something like what Tom and Tom do, where there's, you kind of imagine that there's some ceiling, maybe it's a long way off, but it's there. And so you can expect to find a trend in beta over time. And then you fit the data to a model that has room for that trend, and then you see if you pick it up. But I think this is relevant because it's been really influential in this sort of exercise has been influential in making the case that like, a real singularity, something that really, really looks like that vertical asymptote, at least until we run into intense like physical constraints, isn't such a crazy idea. It would just kind of be a resuming of a trend that existed over the long past. And I think qualitatively that's right, and it's a good point. But then there's all these attempts to like make it more mathematical, which are a little bit made up. Anyway, yeah. Well, let's let Tom say a bit about this hardware software model.
Yeah, so I'll just present a couple of slides from this. It's part of a project with Tom Davidson, Basil Halpern, and Anton Koronek. And I think these slides will be available in the participant guide. So like if you want more information, just look at that. But I'll just present a couple of highlights. which is basically that we kind of get a model that incorporates kind of technological feedback loops and economic kind of feedback loops. And we want to get to the same threshold that we were looking at before with the kind of Cobb-Douglas thing. We want to calibrate that to some features of like AI progress, most notably that kind of we assume it's just a function of progress in like algorithmic progress combined with progress in like computing technology, and also like more greater investment available in computing technology. And the thing that we kind of get to is that, so F terms here are like the fraction of tasks that are automated in a specific sector. So this is like fraction of tasks that are automated in software research. And this R term is just that lambda on beta, which is kind of governing the returns to research effort in those sectors. And we just, this kind of final result we get is going to be that, this thing here kind of just has to be greater than 1 in order to kind of kickstart this kind of hyperbolic process. And in the model, we'll kind of assume that these F terms are just fixed. So we're just saying, but recognizing that automation is like a progressive thing, like we're increasingly able to automate parts of the economy. I'm just going to say that let's just conjecture that these kind of Fs are fixed in stone. And just like once we kind of automate up to that point in real life kind of thing, that's when like we start kind of getting this kickoff. So what does this look like? So this is just kind of recap of what Phil introduced before. The kind of thing that we're doing slightly differently here is going to be that so kind of Phil had a law of motion for technologies, and then had just like we had a K here that wasn't a kind of a K dot, there was a derivative here. We're going to do something slightly differently where we want to consider like a system of differential equations. This is mostly because we're going to consider multiple laws of motion for multiple technologies, so multiple versions of these A's. And we're also going to, so that's like the reason in which we are going to introduce kind of a new kind of method for determining hyperbolic growth. But as part of this, we're also going to have a slightly different version for capital. So this is just going to be capital law of motion with kind of no depreciation. So every period, we're adding some fraction of output to our kind of capital stock. And then the kind of proof method we're going to use here is something slightly different, which is just that if we have a kind of system of differential equations that look like this thing up here, we have this kind of method for determining whether it's going to be hyperbolic growth, which is just if the eigenvalue of this kind of the exponent matrix is greater than 1, don't worry about it too much. But if you're interested, I can talk more about it. And there's also some other methods as well that you can use, but you can just ask me after. And so what are we doing? This is just what Phil's already done. And this is combined with this bit here. So this is the kind of zero model where kind of effective labor is some function of AI labor and human labor. And the exponents just are determined by how many tasks you can automate. So AI can do Fi fraction tasks, and then humans just do the rest. So this is our kind of labor function. So I'll just combine this with some model. Actually, maybe it's easiest just for me to say this. So this is the model that we're going to investigate. So this is the kind of normal Cobb-Douglas output function, except for that we have effective labor replacing normal labor. We have these two accumulable factors, so I'll just run through what the letters mean. So this is just normal capital accumulation. C, I'm going to say is our stock of compute. So maybe it's worthwhile saying here. So we have a term AI, which is just a combination of kind of software levels and hardware levels. Our hardware is a combination of both kind of investment in buying chips. So it's just low C, and our kind of quality of hardware kind of amplifies. So it's like you spend $1 on chips. If you amplify the quality of hardware, then that $1 is just going to get you more chips kind of thing. So that's what H is doing. so we kind of have two stocks, which are just normal capital and kind of the money spent on chips. And we have kind of two technologies. So that's these things here. Oh, so we have three technologies, which is kind of normal TFP. And then the two relevant AI technologies are just software and hardware. So hardware quality and software quality progress through research into kind of hardware and software quality. Yeah. Sure.
Chips are do previous chips still appreciated?
In this, no, I'm just saying, which is a limitation of, so in a more complicated version, we could say something about depreciation. In this, I'm saying there's no depreciation at all, which especially with chips, I recognize that's like a big limitation.
Wait, but there's no depreciation, but you do the thing of saying that it's only C dot that gets augmented by
Oh yeah,
by the age of the
yeah. So it's like so old, yeah. And then so we also have this kind of normal, well, the usual kind of semi-endogenous law of motion for technology. And then we're just combining this with the AI automation term, which is just human work here. And this is the kind of combination of AI, so that's software quality, hardware quality, and chips. And so we're automating in each of these kind of sectors, like including TFP, software, hardware, and output. So that's what the kind of, so there'll be 4 different versions of this AI automation for all the sectors that we can automate. And yeah, so I recognize this is just a very high level thing that I'm kind of getting into here. So I'm just going to say, yeah, this is the background and how we kind of get to this explosion condition. So this is just combining the two, combining this kind of eigenvalue proof method with once we substitute in all of the relevant kind of equations into these set of equations. And so this is kind of what we come up with, which I already kind of introduced here. And then the only thing we're kind of left to do for us is we just calibrate this explosion condition. So we're using these estimates here that we've kind of already been through. The notable ones are that just because of Moore's law, like this, like hardware progress has just been super productive. And we also incorporate an estimate for kind of algorithmic progress. Generally, this comes from like Stockfish is a kind of chess engine. So this comes from that, and roughly this is like much less productive than hardware research, but kind of much more productive than the typical estimate of research productivity across the economy, which is the TFP one here. And so all we're doing is just substituting kind of these terms into the relevant explosion threshold conditions up here. And then, the kind of rough version of what we could be thinking of for an explosion condition is, this is that kind of heuristic is something like you just have to automate, or like a kind of unit of automation of general TFP counts for about half of that of an automation of a task in output or software. And an automation of a task in kind of hardware research counts for about 5 times that of output or software. And the kind of takeaway from this is if you automated, like if all these Fs were the same, I think you just need to automate about 13% of tasks for us to be on the hyperbolic growth path. Yeah, I think that's the main takeaway. There's lots of limitations to this kind of stuff, but I think they're still getting at something interesting. But maybe welcome to talk to me if you have thoughts or questions and stuff like that.